In this video, we are going to implement CycleGans using TensorFlow. First of all, let's download the dataset from Kaggle. I have found out that downloading the public dataset from Kaggle even doesn't require that extra 2 steps of uploading kaggle.json and everything else. So you can directly use this exclamatory sign and then Kaggle and give the link. So the dataset has been downloaded. Unzip it. So these steps are what we have done in the pix-to-pix architecture. Import the libraries TensorFlow, Matplotlib, NumPy, and OS. Define the image directory. So I'm going to use the train dataset for training the model. And this is the split real fake function which we have written for the previous pix-to-pix GAN architecture, reading an image, decoding it, then splitting that image in the center and returning both pieces. This is going to be our preprocess. In the preprocess, firstly I'll call this split real fake, then I'm going to convert data type to float 32, normalize them by dividing with 255 because the max pixel value is going to be 255, and then return the input image which I'll give as an input to the model, and this is going to be the real image or what I want the model to produce. Now these 3 lines of code is going to create the dataset for me. So join the folder path with these image names and then convert them to TensorFlow dataset using from tensor slices and apply this preprocess function on each slice. So we did these 3 steps in the previous video as well. Let's batch this dataset. Let's show some example from the dataset we have just created. So yeah, this is going to be my model input, and this is going to be the expected value from the model. So in case of CycleGan, actually these two are going to act as an input and as an output, and we will see why. And if you have watched the previous video, you know the reason why these 2 images are going to be input at the same time output, because of those forward and backward pass. Now to implement or create the structure for CycleGan, we are going to use the UNet. In the original paper they have used the ResNet, but I'm going to stick with the UNet because I don't want to write the ResNet code. So let's copy and paste the upsampling block of UNet, then the downsampling block. So I did nothing important in these classes except that I have moved this convolutional layer to this build function, which is going to build this convolutional layer the moment our input shapes are known. And the reason for doing this is that we were getting no gradient found errors in TensorFlow version 17, so that's why I have moved them to this build function. Now this is going to be the generator. It's the exact same code, we haven't changed anything. And this is the discriminator, except that we have removed that final sigmoid activation function because instead of using binary cross entropy, we are going to use this mean squared error as discussed in the previous video. And now let's create our utility show images function. And finally, it's time to create the training loop. So we are going to follow a very different approach for creating the training loop in case of CycleGans, and the reason for this is that if you have noticed in the previous videos, we were getting that warning like the TensorFlow framework was retracing the graph, which is computationally expensive, and it's expensive for the memory as well. And if you also have noticed that the longer you train the model, the more memory the model is going to take, and that was because of that retracing process. And we have found out that the retracing was being happening due to that switching between the discriminator trainable weights. So in the same loop, we were first switching them on and then we were switching them off. So these two steps were causing retracing, which is very expensive. So in order to avoid that retracing, we don't have to use that train on batch method. So if we aren't using that train on batch method, then the second option we have is the gradient tab. So in this video we are going to use the gradient tab for training the CycleGan, and you will actually see that the memory consumption will be very optimized in this case. So to create the training cycle with gradient tab, first of all we need a loss function. So in this architecture we are going to use two different loss functions, the mean squared error loss function and then the L1 loss function. So let's create first the object of mean squared error, and now we need to create the loss functions which we are going to use with the architecture. So if you remember, we need two discriminator loss functions, a cycle loss function which will calculate the L1 distance, and an identity loss function. So in total we need four loss functions here, and this is how they are going to look like. So this is going to be my generator loss function. It is going to pretend to be real. That's why we are going to produce this tf.1s like based on this discriminator generated output. So based on the outputs of the discriminator, we are going to train the generator, and we are going to pass those discriminator outputs to this function, and this function is going to find out the shape of this discriminator generated output and will create a matrix of ones of the same shape as this discriminator generated output. And then we are going to find the mean squared error, and then I'm going to find the reduce mean, because remember in this case the discriminator is not a simple discriminator, it's a patch GAN discriminator. So this tf.reduce mean will give us the average value over the batch dimension, but we also need to average over the other dimensions, width, height, and the channel, because the shape is going to be 29 by 29 by 1. And then we need the regular discriminator loss function, which is going to compare the real outputs with the ones and the generated outputs with the zeros, and this will give us the real loss, the generated loss, and I'm going to sum them and will multiply them with 0.5. It's like I'm averaging it. Okay, and then we need the cycle loss. So we are going to use the cycle loss in the forward pass as well as in the backward pass. So I'm going to provide the real image and the cycled image and the lambda. So the lambda is another hyperparameters, and in the original paper its value was recommended 10 for the cycled images, and for identity loss its value was 5. So I'm going to find the L1 distance between this real image and the cycled image, and it's really easy. Just subtract these two values and find the absolute, then reduce mean, and then multiply it with lambda. Simple as that. And then this is the identity loss, the real image, the same image means the one generated by the generator, and then subtract them, absolute, reduce mean, and multiply it with lambda identity, which is going to be 5 in this case. So these are my loss functions which we are going to need in the training cycle. And the training cycle or training step is going to look something like this. Don't worry, let me explain step by step. It's actually very straightforward. If you know the image from the previous video, then this code is no more difficult for you. First of all, we are going to provide our generator AB, which is going to translate A image into B image. Similarly, generator BA. Then we need discriminator A, discriminator B. We are also going to provide the image A dataset. It's like the whole batch of images A. And then the images B batch. Also the optimizers for the generator and optimizers for the discriminator. Once I have all of these arguments, then I'm going to create this gradient tab by also setting this persistent to true, because we are going to use this gradient tab multiple times. So if you don't set here this persistent to true, then after calculating the gradients one time they will vanish. We don't want them to be vanished, we want them to be persistent so that we could use them multiple times. And I'm going to call it as step. And first of all, in the forward pass, what I'm going to do is to pass my image A to the generator AB, which is going to return me fake B, and then I'm going to pass that fake B to the generator BA, which is going to return me the cycled A. So this is the forward pass step. Now in the backward pass, what I'm going to do is to pass image B first to the generator BA. It is going to return me fake A, and then that image fake A to the generator AB, which is going to return me the cycled B. So this is the backward pass. Now we need an identity pass as well. For this purpose, I'm going to pass image A to the generator BA, because this generator B is designed to translate B to A, not A to B. So it is going to return me the same A, and I'll pass image B to generator AB, which will return me the same B. Once I have these three passes, now I need to pass these images to the discriminator as well. Firstly, I'm going to pass the real image batch A to the discriminator A in order to get its score, and then I'm going to pass the image B to discriminator B to get the real B image score. And then I'm going to do it with fake images. So I'm not going to pass the cycled images, rather I'm going to pass these fake images. Okay, so fake A to the discriminator A to get the score for fake A, and then fake B to the discriminator B to get fake B score. Once I have all of these scores and outputs, all I need to do is to calculate the losses. So first of all, I'm going to calculate the generator loss. For this purpose, I'll first pass the discriminator fake B, which will return me the generator AB loss. This generator loss will help us train generator AB, and similarly this generator loss is going to help us train the generator BA. Once I have these losses for the generator, then I need to calculate the cycle loss. So I'll provide the actual image A and the cycled A in order to calculate the L1 distance between them, and similarly the B and the cycled B, and then I'll sum them to get the total cycle loss. Once I have the total cycle loss, all I need to do is to sum them all. So the generator AB loss, the total cycle loss, plus the identity loss, so the image B and same B. Because you can see that we have generated this same B using the generator AB, and now we are calculating the loss for the AB. That's why we are going to use this image B. So I'm going to calculate the identity loss for it. This will give me the total loss for the generator AB. Similarly, I'm going to calculate for generator BA. Then I also need to update the weights of the discriminator. For this purpose, I'm going to calculate the discriminator loss based on the scores for the real image A and the fake A. Similarly, I'm going to calculate the loss for the second discriminator. And once I have all of these losses, then I'm going to first find the gradients for generator AB by using tap.gradient, and by passing first the total loss and then the weights of this generator AB. Similarly, find the gradients of generator BA by passing the total loss for generator BA and its trainable weights. This is going to return me the gradients. Now calculate the gradients for discriminator A and B. Once I have these gradients, all I need to do is to update the weights of the generator AB, generator BA, discriminator A and discriminator B. For this purpose, I am going to use my optimizer, which I have passed as an argument to this train step. Apply the gradients and then zip the gradients with their weights, which I want to update. So this is going to update the weights of generator AB and generator BA. Similarly, I'll do the same process for discriminator A and discriminator B by using their optimizer and zipping their gradients with their trainable variables. So in this training step, you can see that we are not switching off trainable variables of discriminator or generator, and this is going to avoid that retracing issue. So let's run it, and this is going to be the train cycle. I'm going to provide generator AB, generator B, discriminator B, data set, and number of epochs. Firstly, I'm going to create the objects of Adam optimizer for each model. Then I'm going to iterate on epochs, and also on the dataset. I'm going to use my train step function which we have created above, and make sure that you should wrap this function in this tf dot function, which is going to execute it in graph mode, and it's faster than the eager mode. I'm going to pass my required objects. It is going to return me the loss. After every 100 steps, I'm going to show the predicted images of generator AB and generator BA. So I hope this is going to make sense, and I have told you that we are going to design a complete new training cycle in the previous video. Let's create now the objects of generator, discriminator, and finally let's start the training process for 5 epochs. And now look to the memory consumptions. I'm going to use T4 GPU in this case. GPU is going to consume like 10 GB, and then RAM is going to consume like 5 to 6 GB for the whole training step. So it's very optimized. I'm also going to give you a sample code of this exact same architecture with train on batch step, and you will observe that it is consuming a lot. I mean like a lot of RAM, and I think after 70 steps I was getting the OOM out of memory issue because the model used to consume all the RAM in the first 75 steps. Here, as you can see, we got our first step. After 100 steps, the model got quite good. So the segments images looks more like segment images, and the real images started looking like real images. The training has been finished, and I have just trained for 500 steps, and we can already see that results are quite impressive. If I zoom in, although the segment masks aren't the exact same segment mask, but still we can see that model is trying to predict at least their colors or their overall structure. And then the real images looks like generated images, yeah. So model is trying its best, but still we are human, we are quite good. So obviously if you train for higher epochs with ResNet, results will get better. And in the next video we are going to talk about another important architecture, and I'll see you there. Bye bye.